Hi everyone, welcome back to another video for heat and mass transfer or transport 2. Today we're going to be talking about the Maxwell-Stefan equations. So the Maxwell-Stefan equations are very important equations when we're looking at any sort of mixture system. So this is a really good way to look at a multi-component system. So whether you have 2 up to 10 or however many components, the Maxwell-Stefan equation allows you to look at how 2 specific components interact with each other, so you can kind of analyze it at a little bit of an easier level, because it's really hard to look at how all of them interact at the same time. So being able to just look at how they interact one-on-one with each other and then see that for each different pairing that you could have, that makes it a little bit easier to analyze your system. So I have my page just written here. I have our agenda for today. Let me change the lighting a little bit so it's easier to see. Okay. Okay, hopefully that's good. Can you see that? Okay. Let me tilt it towards me, maybe. How is that? That is not much better. Okay, there we go. That's the best, I think. So, I'm still in frame here. Okay, so I've just written here our agenda. So we're talking about the Maxwell-Stefan equations, which this is it written out right now. And then we're going to talk about the relevance, which I kind of already touched on. So once again, this is good at looking at a multi-component system and analyzing how 2 of those components interact with each other, to kind of simplify it down a little bit and look at it as if it's a binary system rather than multi-component. So this is a really important equation, and it relates to a lot of different areas of mass transport. So this equation can actually be simplified into terms of velocities. So we're specifically looking at the equation relating to liquids, but you can look at the equation relating to gases as well. You just have to change the mole fraction that you're looking at. But we're going to look at how this equation simplifies into the component velocities, so how these velocities of the liquids can relate to the flux. And then we're also going to look at how this simplifies if we're looking at an ideal mixture when it's in a pure state. So pure state just means that the mole fraction is going to be equal to 1 or 100. 100%, sorry, that is. And then lastly, we're also going to see how this can relate to Fick's law, which is something that we've talked about a couple of times now for mass transport. So the first thing I'm going to do is kind of just run through what each of these symbols mean. So I'm just going to go ahead and rewrite the left side of the equation, and this list over here is just everything that we're going to talk about. But I just rewrote the left side of the equation, and we're going to go ahead and look at each of these. So the first variable we have is xi. So this is going to be our mole fraction. And that's probably something you recall from other videos. The subscript I just means the mole fraction of the I component. So when we look at this Maxwell-Stefan equation, you're going to see there's variables I and variables j. And so that relates to the two components that we're seeing how they interact with each other are I and j. They're just denoted as that. And then next to that, we're going to have this really weird upside down triangle. So you've probably seen this before as well. You'll recall it means gradient. So it's analyzing the gradient of whatever the next variable is. And if you remember, gradient is kind of similar to a like when we talked about Fourier's law, concentration gradient. That just means that there's some sort of change as you move due to position. So that's our driving force for change is as we move positions, there's going to be some sort of concentration change, some gradient change. And we're looking at the gradient of the next symbol is mu, which is chemical potential. This is something that was also mentioned previously. So chemical potential of I. So we're looking at the chemical potential of component I and how it changes throughout this mixture. And then on the bottom, we just have our constant there, gas constant. And then temperature equals. And then we have our sigma, so sum when j equals 1, number counter, xi and j minus xj and I. All right, so I just have arrows pointing everything that we pointed out here on the left side of the equation, and then I've rewritten the right side. So now what we're looking at here is, so that's going to be the sum of all of the other components that we're looking at compared to I. So I is our main component that we want to look at in this multi-component system. J is denoting which component we're looking at in comparison to I. So it's like, for example, if we just give them a number denotation. So I is going to be the first component in the system. And we have, I'm sorry, my nose is itching me really bad. I is going to be our first component in the system, and we are going to have 5 total. So that right side is saying we're looking at 1 compared to 2, added to 1 compared to 3, 1 compared to 4, 1 compared to 5. So it's just the sum of all of those comparisons of 1 to every other component in the system. And then you could go back and look at it for component 2. So you do component 2 compared to 1, compared to 3, compared to 4. See what I get the idea there? So that's what that means. And then we still have the xi here, so we recall that x is the mole fraction once again. Oh my gosh, my nose is killing me. And then the big N is going to be our flux. C in the denominator is our total concentration. And the Dij is going to be the diffusive coefficient. So that is something that is found experimentally. So that considers how whatever component you're looking at diffuses into the other component. So that's something that we have to determine experimentally, and once again is a coefficient or constant. So it will be constant, and that is usually something that you can find online because it's common knowledge because they've been found experimentally. So that's kind of looking into what is the Maxwell-Stefan equation, what is it consisting of. So you can just see that right there. Those are all of our variables defined. Really quick, I'm gonna write the gas version of this. So this is our liquid version right now. And I'm gonna go ahead and write our gas. And the only thing that's gonna change, as I mentioned before, is that the mole fraction is gonna be represented by a different letter, because mole fraction of liquids are x's, and then the mole fraction of gas is represented by y's. So it's gonna be essentially the same equation, just instead of x's, we'll have y's. So I'm just writing that out really quick. And I'm writing this out because when we're looking at the velocity and how the component of velocities are directly related to the Maxwell-Stefan equations, we're going to look at that in the gas phase. So I'm just writing this out so we have it for that next part of the video. All right. So once again, the only thing that I changed is I made the x's y's. And this is gas. So I'm going to go ahead and simplify the left side of the equation by writing it as the driving force of I is equal to the right side of the equation. So that gradient with the chemical potential is, as I mentioned, the driving force. So that's what is really changing when these two components are mixing together. And so I'm just going to simplify it down to D with subscript I to represent the driving force of I is equal to our right side of the equation. And this is kind of just to make it easier for us to write everything out, because it gets really redundant writing all of those variables out. And right now, the left side of the equation is not necessarily important to us with what it's made up of. We just need to know that it is the driving force of I. So again, I'm representing that as di, and then is equal to the right side of our equation. So that's just going to remain the same. And now I'm going to write what the equation, the Maxwell-Stefan equation is, when it is represented in terms of the component velocities rather than the fluxes. And then I'm going to show how we can get from one equation to the other and how they are directly the same equation, just represented by different variables, different units of measurement. So I'm going to say di, so our driving force of I, is equal to, we still have our sum, y equals 1 to n, but this time in the numerator, we're going to have yi, so mole fraction of I, times yj, mole fraction of j, and then is multiplied by the velocity of component j minus the velocity of component I. And all of this is still going to be over the diffusive coefficient ij. All right. So what I've done here is I just simplified our original equation here to make the left side equal to the driving force of I. And then over here, this is the Maxwell-Stefan equation represented in terms of the component velocities. So we can notice two big changes here. So the first is that instead of the fluxes in the numerator, we now have velocity. And along with that, we also don't have the concentration in the denominator anymore. So what we're going to do is we're going to try to make this equation look like this one. So if we want to do that, then our first step is to add this concentration back in. But in order to make this feasible and remain it the same, because we can't fundamentally change the equation. We can't just decide, okay, we're going to add concentration back in that denominator. You can't do that because you're changing the actual equation and what it means. So in order to keep this the same equation, but still add the concentration back in there, is we have to multiply the top and the bottom by concentration. So I'm going to go ahead and do that. I'm going to write a 1 next to this, so like the first step in getting that second equation with the velocities back into the original equation with the fluxes. So di is going to equal our sum. And now we'll have concentration on the numerator again, yi, yj, vy minus vi, all over the concentration times dij. So now this is looking a little bit more familiar. So we have our concentration back in the denominator, so our denominator looks great. Now our numerator is looking a little funky, so we need to try and change this up a little bit and get it to look like the numerator from the original equation again. So what I'm going to do is I'm going to factor in these three variables into each velocity component. But I want to point out something first. So if you do the concentration of your entire component, so like everything that you're looking at with I and J, and you multiply that by the mole fraction of I, what do you get? So if you really think about it, you have your entire concentration, and you're multiplying it by however much of I that you have. So that's going to equal the concentration of I. And then it's the same thing for J. So you take your entire concentration and you multiply that by the fraction of how much J you have. And that's going to equal the concentration of J. So when we factor in those variables, we're going to go ahead and change so whenever we factor in and multiply it against the velocity of J, we're going to go ahead and factor in that concentration and make it the concentration of J too. So then we have concentration of J, velocity of J, times velocity of I. Times mole fraction of I. So second step, that probably sounded like a lot, but I think it'll make sense when you see it. So now we're going to have okay. So I had written on the side here that if you do, the total concentration times the mole fraction of I, you get the concentration of I. And then the concentration times the mole fraction of J equals the concentration of J. And then now I did our factoring step plus changing the total concentration to concentration of J times velocity J. And then we still have our mole fraction of I. And then the mole fraction of J is still here, concentration of I, velocity of I. And then here we still have our denominator the same. So we're slowly but surely getting there. You'll notice that we have yi here in the original equation and yj, and we already have those here, yi, yj. Now we just need to simplify the concentration of J times the velocity of J to equal the flux. So luckily, that's exactly what what flux is. So flux is going to equal the concentration of whatever component times the velocity of that component. Because when we're looking at flux, we're trying to look at some sort of flow. So that's going to be our velocity. And we're also looking at the concentration, so kind of the area that we're flowing through. So that includes our concentration term. So the flux of I is actually equal to the concentration of I times the velocity of I. So our third and final step is to simplify this. So di is equal to our sum. Now we have yi times nj minus yj times ni over concentration dij. So we can see that these two equations match now. These two. So these look exactly the same. So this is proving that if we put this Maxwell-Stefan equation in terms of our component velocities, it is equal to the original equation with the fluxes. So that was the second part of the video where we looked at the component fluxes. And now we're going to look at how the Stefan-Maxwell equation relates to the molar flux. So that's going to be represented by our letter J. So like I said, we're going to find how this is also going to relate to our molar flux, which is the J variable. So if we want to write our total flux, say we're looking at the total flux of I, I'm just writing this on the side here, that is equal to the molar flux of I plus the concentration of I times the total flux. So this is kind of a similar ideal to the concentration, the total concentration times the mole fraction of I that we just talked about, how the total concentration times the mole fraction of I is equal to the concentration of I. It's kind of a similar situation here for the flux of I. So the flux of I is going to equal the molar flux of I that we're looking at. So this is how the moles are moving through this component or through this system, plus the concentration of I times the total flux. So that's going to equal the flux of I, those two added together, because you're considering the flux with the concentration of I plus how the moles are moving too is the total concentration of I and that flux. So I explained that really poorly, but this is the equation here that we're looking at. And we can recall that the concentration of I is equal to the total concentration times the mole fraction of I. And we're going to actually write that as that because it makes it a lot easier for us, or it makes it easy for us to simplify. So Ni equals Ji plus total concentration times mole fraction of I times the total flux. So we've just rewritten it with the concentration of I in that expanded term of the total concentration times the mole fraction. And now I'm going to go ahead and reset the steps and start from our beginning equation, which is the one right here, and substitute in, instead of the flux, we're going to substitute in this equation for flux. So we'll start by doing that. Driving force of I is equal to our sum. Excuse me. Okay. Oop. I wrote my J backwards, I just realized. Alright, so now we have this equation here. So I substituted in that equation for the flux. So we have mole fraction of I times, in parentheses, our molar flux of J plus the total concentration times the mole fraction of J times our total flux minus the mole fraction of J times the molar flux of I plus total concentration times mole fraction of I times total flux. And then our denominator remains the same. So now I'm just going to go ahead and factor in this mole fraction of I to here, and then same thing for these two terms. And we'll write that out fully. So driving force of I, sum. Now we have Yij plus Yi C. Well, actually, I'll put both the mole fractions next to each other because it's just easier. Yi Yj Cn minus Yj Ji minus, because you have to distribute that subtraction in as well, Yj Yi Cn all over Cdij. Alright, so now we have our expanded out parentheses, and this looks pretty complicated, but if you really look at it more closely, you'll see that these two terms actually cancel out. So this is the same term. So these can cancel, and then we're left with our final equation, which is just showing how this equation relates to molar fluxes as well. So we can cancel these, and then I'm just going to write down at the very bottom here what this final equation is. So it'll equal the sum yi, so mole fraction of I, times the molar flux of J, minus the mole fraction of J times the molar flux of I, and then still over the concentration times the diffusive coefficient. So there we go. So that's just showing how the component velocity is related to the Stefan-Maxwell equation, and then how our molar flux is related as well. So now we are going to talk about how this will simplify if we have an ideal mixture in a pure state. So I'm going to start by rewriting our Stefan-Maxwell equation, and we're going to be looking at the main one, which is the first one that we started with the fluxes. So we'll have yi, because we're going to talk about gas, or actually, we will use, we have to use no, she uses x. Okay. So I'm going to start by rewriting our Maxwell-Stefan equation, which is the first one that we started with, the main one. So we'll have xi times our gradient times the chemical potential of I all over RT. It's equal to our sum, J equals 1 to N, and then xi and j minus xj and I over concentration and diffusive coefficient. So this is just our starting equation again, rewritten. And once again, we're looking at this ideal mixture in a pure state. So first we're going to address the fact that this is a pure state. So that is going to affect one of our variables here, and that's specifically going to affect our chemical potential variable. So if we have something that is in a pure state, that means that the chemical potential is going to be equal to its reference chemical potential. So our chemical potential of I will equal the chemical potential of I at its reference state, which is represented by this 0 here. And chemical potential, the gradient of chemical potential is just showing how our chemical potential of I is changing over a position, because it's the gradient, it's the driving force for change. But the chemical potential in our equation cannot be equal to just the reference state of the chemical potential, because they're typically not equal to each other. So in order to consider that they're usually not equal to each other, we have to add some sort of additional term to the reference chemical potential in order to make them equal. So we're going to add the gas constant, R times temperature, T, times the natural log of our mole fraction of I. So this addition is going to consider the fact that the chemical potential is not going to be equal to the reference chemical potential in normal circumstances. And since we're looking at a pure state, we want to look at the reference chemical potential. So, like I said, this needs to be multiplied by the gradient and the gradient is equal to some sort of change in the chemical potential, so D times chemical potential of I, over the change in position, so over dz. So this is something we've seen many times before with some sort of concentration gradient where it's changing due to position. That's what's happening here. But since we're substituting this equation in for our chemical potential in this equation, we need to take the derivative of this equation and get it so that we can substitute the gradient of chemical potential of I back here. So we can write d over dz times our new equation for chemical potential of I, which is equal to the chemical potential of I at its reference point plus RT natural log of xi. So now we can take the derivative of this. It's going to equal, so that reference chemical potential is going to be a constant. It will not be changing due to any sort of mole fraction, any sort of position change. That's a constant no matter what. So it will go to 0. Same thing with our gas constant. It is a constant. Our temperature is also going to remain the same. And then the only thing that would be changing is our mole fraction. So the mole fraction of I could be changing. So we'll take the derivative of the natural log of xi, which will just be 1 over xi. And then we're still going to have this times dxi over dz. So I can show you here how this has simplified. So we took that derivative, and then we're taking the derivative of that xi because the mole fraction is what would be changing in this equation. And that's why we took the derivative of the mole fraction and then still with respect to the change in position. So now we're going to take this and plug it back into our original equation. So now we have mole fraction of I times RT 1 over xi dxi over dz all over RT, and then equals our right side of the equation, which we will not touch. All right. So I've just plugged that back in, and you'll probably notice that we can start canceling some things on that left side of the equation. So those RTs are going to cancel out, and the XI will cancel out. So we can go ahead and do that. RT, RT, XI, XI. And we're just left with the derivative of our mole fraction of I with respect to a change in position equals the right side of our equation, which remains the same. So what this is showing is that when we have an ideal mixture at a pure state, we don't have to look at the change in chemical potential because it is a pure state. And the only thing that's going to be some sort of driving change in this particular situation when everything has been simplified is that the mole fraction of I is going to be what is our driving force for change. So that's going to be what is changing due to position, and how that is equal to the mole fraction of that and component J times fluxes. So it's kind of just showing us how our driving force for change is simplified down due to the fact that this is a pure state and an ideal mixture. For the last part of the video, we're going to see how this instance with the ideal mixture in the pure state can simplify down into fixed law again. So if you recall, Fick's law relates the molar flux. So that was represented by the J variable, which you'll recall earlier in this video, we found, we found this equation with the molar fluxes. So we're going to go ahead and write that again, that our driving force of I is equal to the summation J equals 1 to n of fraction of I times the molar flux of J minus the fraction of J times the molar flux of I all over concentration of I, J. So that's just rewriting our equation that we found earlier this video, that our driving force is equal to that right side of the equation with the molar fluxes instead of total flux. And now, since we know that this is an ideal mixture, pure state, we know that our driving force was equal to this. And we already showed how this is equal to this, so we don't need to do anything on the right side here. We can substitute this in as our driving force variable down here. So we'll have d, I'm going to go ahead and change the x into a y, so that we know we're going to be looking at a gas state now, because that's what we have our right side of the equation is in the gas state for the molar mole fraction. So we're going to change the x to a y, and that wouldn't change anything relating to how that equation is set up. So we're just going to do dyi instead of dx. Still over dz, because no matter what, the position variable is going to be z. And then we have that equal to our right side of the equation once again. So in order to simplify this into Fick's law is in regards to a binary system. So we're going to simulate how the summations work if we're looking at a binary system. So that's when J can be equal to 1 or 2, because we're looking at either one component alone or one component and 2 together, because that's a binary system, is 2 components. So we're going to simulate how that summation looks like. So on the left side, I'll show you really quick how we substituted that in. Just change the driving force into this, which is what we found right here just a second ago. So now we're going to simulate. I is always going to be equal to 1, just to make it easy. We're looking at the first component in our system, so I equals 1. So dyi dz. Actually, I'll go ahead and substitute in 1 here for I already. So now we're going to start with J equaling 1, because that's where we start our summation. It's going to go until 2, because we're looking at 2 components, a 2-component system, a binary system. So as I said, J could equal 1 or 2. So we'll start with J equaling 1. We have y1, so substituting that 1 in for I, and then j1 as well, substituting j in for 1, 2. Minus y1 again, j1, all over c d1, 1. So this is the first piece in our summation where j is equal to 1. So all of these subscripts are going to be 1, and you'll notice that the numerator will cancel out. So this first term is going to equal 0, which makes complete sense, because you can't have some sort of change in molar flux if you're only looking at one component. We're trying to see how these 2 components mix together, how the fluxes mix together, how they diffuse. And so if you're only looking at one component, how it's diffusing with itself, it doesn't make any sense. It's not going to be diffusing with itself. So that makes sense for that first term to equal 1. Our second term, we can plug in j equals 2 now. So we will have y1 j2 minus y2 j1 over our total concentration times how 1 diffuses in 2. So this is what we have here. I'm going to go ahead and write the arrow to cross out that first term. So we know that first term equals 0, and then we just substituted j equals 2 for the second term. So now we can write this as dy1 over dz equals y1 j2 minus y2 j1 all over the concentration times the diffusion coefficient or constant. So now we're going to begin simplifying this. So you'll recall that for mole fractions, the mole fractions of all of our components in a system are going to equal 1 because you can't have more than 100%. And each of these mole fractions relates to some sort of percentage of the whole. So mole fraction of 1 is what percentage of the entire thing is made up of component 1. So we can recall that y1 plus y2 will equal just 1. Because we have a binary system here, there's only 2 components. The mole fractions of each of those pieces has to equal 1 total. So this is helping us simplify our variable into, instead of having y1 and y2 variable, 2 unknowns, we're making it 1 unknown instead. So we'll write y2 in terms of 1 minus y1. So we can plug that back in, get rid of one of our unknowns. Similarly, we can get rid of one of our molar flux unknowns as well. So when we have a binary system, it's at steady state, there's not going to be any sort of change in flux. The fluxes of those 2 components have to equal each other because they have to equal the negative version of each other because the total molar flux will be equal to 0, and then you have to add up the pieces of your 2 components. So 0 will equal the piece of component 1's flux plus the piece of component 2's flux. So they must be the negative version of each other. And this is because it's a binary system at steady state. So we have 2 simplifications here to get rid of 2 of our unknowns, and we will go ahead and plug that back in. So dy1 dz equals, y1 will remain the same. j2 is now going to be equal to negative j1 minus y2 is now equal to 1 minus y1, and j1 will stay all over cd12. So we've just plugged that in right here. We can go ahead and factor in that j1. So we'll have negative y1 j1 minus j1 plus y1 j1 all over cd12. So I've just written this down here. So now we can see that the y1 j1 will cancel, and we have dy1 over dz equals negative j1. I'm going to go ahead and get rid of, our subscripts. So we have dy over dz equals negative j over cd. So this should be looking very familiar to you. If you recall Fick's law, we just need to rearrange this just a little bit to be j equals instead of dy dz equals. So we'll get J equals negative CD dy over dz. And this is exactly what Fick's law is right here. Our molar flux equals the negative total concentration times our diffusion coefficient times the concentration gradient, molar. It's the molar concentration gradient, but concentration gradient regardless. So, as we can see through this video, the Maxwell-Stefan equations are very versatile and very useful when we're talking about mass transfer. It can relate to Fick's law. It can simplify down when you have a pure state with an ideal mixture at steady state. You can see how it relates to our velocities, component velocities, and molar fluxes as well. And it's very real world applicable. It makes it really easy to look at a multi-component system and really analyze how it's actually interacting with each other. So that's going to be everything for this video. Hope you enjoyed.